In this video, we will be discussing aspects of linear algebra, talking about elements of matrices, determinants up to higher order matrices like the 4x4 matrices. We'll also be looking at inverses of matrices using different methods, particularly using the adjoint method as well as the elementary row operations method. Linear algebra is a powerful tool for solving problems of linear equations, and it helps in the manipulation of a lot of mathematical problems. So it mainly deals with the study of vector spaces, linear equation, linear transformations, matrices, which includes inverses of matrix, determinants, and so on and so forth. Now, a matrix is a rectangular array of numbers arranged in row and columns, and it is usually denoted by a capital letter, italicized. Capital letter A, B, C, D, Z, and so on and so forth, really. So now, and in form of this type of enclosure, where you have a number of elements, we call what you find in here as the elements of the matrix, and the unique position of each of the elements can be identified by the row and column it falls into. So for the elements in this first row, we call it row 1, row 2, row 3. So m is usually the number of rows and n is usually the number of columns. So for this first element here, it can be identified, its unique position in the matrix can be identified by the row and column it falls into. So it is written in this form, element A subscript 1, 1, showing that it falls in row 1, column 1. So this second element here is found in row 1 and column 2. This is column 1, column 2 up to column n. This is row 1, row 2 up to row m. So this element is found in row 2, of course, and column 1. So kindly take note of the fact that the row is usually the first written in the subscripts. So you represent this element as row 2 first. So m usually, which is the number of rows, comes before n, and that is why for this element in let's say an unknown position can be identified by the specific value of the row and the specific value of the column. So the row here is the m and the column is denoted as n. So now if a matrix has m rows and n columns, it is called an m by n matrix. So for example, take for example this matrix. So this is a 2 by 3 matrix because it has 2 rows and 3 columns. This is the correct guy there. I think this is just an oversight. So please, it is row first and column. So this is not multiplication. It is just denoting the representation of this matrix as m by n. So a 2 by 3 matrix, showing that the matrix has 2 rows and 3 columns. All right then. So we move on to types of matrices. We can have square matrix, diagonal matrix, identity matrix, zero matrix. We can also have transpose of a matrix. So let's just explain this one after the other. A square matrix, of course, is a matrix with the same number of row and column. So I think that is clear. So take for example, if you have 3 rows and 3 columns, we call that square matrix. And that shows that this example here, matrix A, is not a square matrix. Okay, diagonal matrix. A diagonal matrix is a square matrix where all of diagonal elements are 0. Okay, so let's say you have a matrix A equal to, and you have a square matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see that this matrix have 3 rows and 3 columns. This shows that this matrix is a square matrix. So a diagonal matrix is a square matrix where all off diagonal, this is the diagonal of this matrix, this. So off diagonal are other elements beside the ones on this diagonal. So when all the off diagonal elements are 0, it shows that this one is 0, this one is 0, this one is 0, this one is 0, 0, 0. So when this happens, all 4, 7, 8, 2, 3, 6 are all 0 each. Then we say we have a diagonal matrix. However, for an identity matrix is a diagonal matrix where all diagonal elements are 1. So now let's assume this is already 0, 0, 0, 0, 0, 0. So it shows that we already have a diagonal matrix. However, this diagonal matrix will be an identity matrix if we now have a unit each along the diagonal. That is 1, 1. So this isn't 5 but 1, and this isn't 9 but 1. So when this happens and the diagonal elements are 1 each, then we say that matrix is an identity matrix. All right, so then for a 0 matrix is a matrix where all the elements are 0, including these ones. Everything will be 0. So now moving on from there, transpose of a matrix. Of course, a matrix can be transposed, and when a matrix is transposed, it is denoted in this form. So let's take this matrix A as an example. We can transpose this matrix, and when we transpose this matrix, it then means that the transpose, you arrange the row in column. You change the rows to column, simply put. So row 1 will simply be the first element in the row will be the first element in the column. The second element in the row will be the second element in the column here, and the third element in the row will be the third element in the column. And so you do that for the next one. The second row here will now form the second column, and the first element in the second row will be the first element in the second column. The second element in the second row will be the second element in the second column, on and on and on. So if that means that what we have at the end of the day is a transpose of the matrix A. So next we look at matrix operation. Various operations can be performed on a matrix, including addition, subtraction, multiplication, and so on and so forth. Basically, the 3 main operations are addition, subtraction, and multiplication. And of course, division can also come into play. So addition of matrix or subtraction of matrix. So how do we achieve addition, adding 2 matrix or 2 matrix together? So say we have a matrix A and matrix B. So what you do is that uniquely the elements A11, that's the first element, the element in the first row and first column, will be added to the first element in the row here and the first element in the column here, that is 6. So this will be added to this, this will be added to this, this will be added to this. So, and that is what we've done here. So it then means that this will also be added to this will also be added to this, and this will also be added to this. So here we add like terms together. So of course, you know, this element is a like term to this element because they occupy the same position. So that is how we achieve that addition operation. And if it is subtraction, you'll simply subtract the element b from what you've got in the element that occupies the like position in the matrix A. So if done correctly, the addition of matrix A and B will give us the values we've got in the summation solution here. Another operation that can be performed on a matrix is scalar multiplication, and that involves the multiplication by a scalar value, let's say k. So let k be 3, for example. If you want to multiply 3, this scalar value, by this matrix, it then will be ka, and that will mean 3a. So it then means that you will multiply 3 by all the elements in the matrix. So the first element here, this 1 will become 3 times 1. This will be 2 times 3. This will be 3 times 3. This will be 4 times 3. This will be 5 times 3. This will be 6 times 3. In other words, you multiply the scalar value with every element in the matrix to achieve a scalar multiplication. All right, so we can also have matrix multiplication where a matrix and another matrix are multiplied together. So take, for example, matrix A, matrix B in this way. So the multiplication of A and B is achieved by the simplest form is to write the matrix A twice. Take, for example, this isn't there yet. So take, for example, this isn't there yet, this isn't there yet. Let me use a difference. So so this is covered, this is covered, this is covered, and this is covered. So you now see that what you have is in form of writing the elements of matrix A twice, 1 0 2 3, 1 0 2 3. So when you do that, so the next thing you then do is then write element, multiply what you've written down. You see, it then means that the row of your new matrix, which will be formed by the multiplication of A and B, will now have 1 2 3 4 elements. So now you arrange the second matrix to be multiplied. You start from the first element here and you go from down the row, 4 6 5 8, 4 6 5 8. So you do same for the second row, which is 4 6 5 8. So when we take this off, you will see 4 6 multiplied by 5 multiplied by 7, 4 6 5 7, and you see this too, multiplied by 4 multiplied by 6 multiplied by 5 multiplied by 7. So you arrange it in this form, and then you multiply out 4 times 1, or 1 times 4 gives you 4, 0 times 6 gives you 0. So when you add that together, when you add what you've got here together, you have 4. So on the second side here, you have 1 multiplied by 5 plus 0 multiplied by 7. So this gives you 0, and you have 5 left here, and that gives you that value. So 4 multiplied by 8 multiplied by 4 gives you 2 multiplied by 4 gives you 8. 3 multiplied by 6 gives you 18. So 8 plus 18 gives you 26. Now this 2 times 5 gives you 10, and 3 times 7 gives you 21. So 10 plus 21 also gives you 31. So that is that. Okay, so moving on, we'll be looking at the determinants of 2 by 2 matrix, 3 by 3 matrix, and 4 by 4 matrix. Of course, the determinants of higher order of matrices can also be determined, like say 5 by 5 matrix, 6 by 6 matrix, and so on and so forth. But then that is a rather complex one. If you know, beyond a 4 by 4 matrix, you've got a rather complex formation of matrices if you want to go higher than 4 by 4 matrix. So if you want to go higher by 4 by 4 matrix, it is advised that you just basically use programming. Maybe you can use programming language like Python to solve that. So that will be easier using programming language than solving literally. So for a 2 by 2 matrix, the determinants of matrix A, take this for example, is written this way: determinant of A. So top to bottom diagonal, you multiply the elements AD minus bottom top diagonal in this form. So it will be AD minus BC. So that gives you the determinant of matrix A, as A is a 2 by 2 matrix. So moving on from there, a 3 by 3 matrix, the determinant of this 3 by 3 matrix is such that you take the first element in the row, in the first row, so you write it down. So the column where that element is found and the row where that element is found, you can cover it in this way. So you'll be left with a 2 by 2 matrix. So what you do is to look for the determinant of this matrix, this 2 by 2 matrix here, and which is this, as determined earlier. So, and that is for the first element in the row. So you do same for the second element in the row, which is this. However, this time around, you alternate the sign from what it was previously. So initially, we didn't alternate any sign for the first element in the row. So for the second element in the row, you use a negative sign and you write down the element B. So now cover what you've got in the column relative to the element and the row relative to the element B. So what you then have also is what looks like a 2 by 2 matrix. You look for the determinant as well, that is DI minus FG, and that is what you've got here. So, and the third thing you do, you also do some same for the third element in the first row. This time around, you also just alternate the sign, positive, negative. This time around, we'll be dealing with the positive sign. So you write down the third element C, then covering the column and the row relative to this element C, you then will be left with a 2 by 2 matrix form. And when you look for the determinant of that 2 by 2 matrix, that will give you DH minus EG. And so this is the way you compute the determinant of a 3 by 3 matrix easily. So assuming you've got numbers in this as the elements in this 3 by 3 matrix, you see you can easily solve for the determinant of the matrix B. Okay, so then let us move on from here to the 4 by 4 matrix. So in the similar way the 3 by 3 matrix was treated, the first element in the row will be considered first, the second element in the row will be considered next, the third element in the row will then be considered, and the fourth element in the row will finally be considered. So what you do is, when you consider this, you just literally consider that element, and by the time you want to consider the second element, you alternate the sign, and by the time you want to consider the third element, you also alternate the sign from the previous one. So this is a negative, this will be positive, And when you want to treat the fourth element in the row, you also alternate the sign from the previous one. That is, this is positive, this will be negative. So now for the first one, first element in the row, you will have to do away with the row relative to the element and the column relative to the element. So what you are left with will be in the form of a 3 by 3 matrix. So you then look for the determinant of that 3 by 3 matrix using the same procedure earlier discussed. And so that will give you this element multiplied by the determinant of the 3 by 3 matrix. So, and the second thing to do will then be you alternate the sign first, and after alternating the sign, you write the second element in the row, first row. That will be A12, A12, that's minus A12. So when you cover this row, this column, and this row, you'll be left with 3 by 3 matrix. So you also look for the determinant of that. So after that, you then alternate the sign again and write down the third element in the row, and you also ensure that you do away with the row relative to that element and the column relative to that element and the row. So what you are left with, do away with the row relative to the element and the column. So what you are left with will form a 3 by 3 matrix. So you also look for the determinants, and that is represented in this way. So, and after doing that, you then do for the third element in the first row. So don't forget to alternate the sign. Very, very important. So from positive to negative, positive, and this would now be negative. So negative of the fourth element in the first row. Then you also cover the column relative to that element and the row relative to that element. So what you've got left will be a 3 by 3 matrix. So you also look for the determinant using the previous method, the previous approach explained, and that will be the determinant of this, and that is how you plug in the values and compute the determinant of a 4 by 4 matrix. Okay, so let's apply what we've just done in looking at some examples. For a 2 by 2 matrix, say matrix C, the rows being 3, 8, and the second row being 4, 6. So to calculate the determinant of this 2 by 2 matrix, what we do is say 3 times 6 minus 4 times 8. So 3 times 6 is 18, 4 times 8, 8 times 4 is 32, so 18 minus 32 gives us minus 14. So let's look for, let's see how to calculate the determinant of a 3 by 3 matrix. Okay, say the matrix is in this form. So the determinant will be, you write down 1, then you say minus 4, you'll be left with this 2 by 2 matrix when you cover the row and the column where the first element in the first row relative to the first element in the first row. So you now have minus 4 multiplied by 9, and this is it, minus 8 times 5, and this is it. So you then alternate the sign, and you have a minus sign here, then you write down 2, then you also do away with the row and column relative to the second element in the first row, and you'll be left with a 2 by 2 matrix that will be 0 times 9 minus 7 times 5, and that is it here. So plus, you do that for the third one as explained earlier, and if done well, the determinant of this 3 by 3 matrix will result in 78. So the third example here will be to find the determinant of a 4 by 4 matrix, this matrix C. So the determinant will be, take the first element in the first row, which is 2, you write that down, and you then cover the elements in the row and column relative to the first element in the first row. So now you'll be left with this 3 by 3 matrix, and it is written here. So you then alternate the sign and write down the minus sign here and write down the second element in the first row, and now doing away with the column relative to the element and the row relative to the element, you'll be left with a 3 by 3 matrix like this. So you do that for the third one and the fourth one as earlier described in the example. Now notice that this here, this isn't 1 but minus 1. So when you alternate the sign and you write minus down, the element here in itself is minus. So you ensure you do not do away with your minus here, because that is tricky. So that will be minus, and at the end of the day you have minus times minus, which will give you plus, a plus. So this example is intentional in order to clear that. All right, so then the determinant of this 3 by 3 matrix is, determined using this previous approach for a 3 by 3 matrix, and that is multiplied out for this second elements in the first row. So it is also, the determinant is also computed and multiplied with the second element. And the third one, which is 0, of course anything multiplied by 0 will be 0, and that is why you see 0 here, simply put down. And for this, which is minus times minus, which will give us plus, so we have plus 1, and the determinant of the matrix, the 3 by 3 matrix generated from that particular aspect is determined here. So if done appropriately, the determinant of this 4 by 4 matrix will result in minus 1 to 5. All right, so let's consider properties of determinants. Property 1. We categorize these properties into 3: property 1, property 2, property 3, for easy explanation. So the first property I'd like to talk about is row or column operation. So row and column operations are usually performed on a matrix or the determinants of a matrix for very, very important reason. And of course, we'll look at some examples as we move on. So rows and columns can be interchanged. So if 2 rows or 2 columns of a matrix are interchanged, the sign of the matrix is reversed, basically. So in other words, what we're trying to say here is that the row and column of a matrix can be interchanged. So when that is done, the only thing that is affected in that matrix is that the determinant of the matrix, the sign is simply reversed. So if it is a 2 by 2 matrix, you exchange the row of the matrix, and just by merely exchanging the row, if you determine if you compute the determinant of the matrix just as it is, then you interchange the rows or you interchange the columns, and you find the determinant again. The determinant you will compute by interchanging the rows or interchanging the columns will be a reversal, or let me just say the negative of the original determinant of the main or initial matrix. Okay, then the second thing that is possible when we want to perform row or column operation is that if a row or column is multiplied by a scalar, the determinant is also multiplied by that scalar. So there are basic things that when you do, particularly when you perform rows and columns operations on the determinant of a matrix, it only helps to probably move towards solving the problem at hand. So it helps you to move gradually towards solving the problem, and it does not really disorganize the formation of the structure of the matrix. So row and column operation can also be performed by scaling, multiplying with a scalar value. Say k can be 1 2 3 4 0, mainly 1 2 3 4, and so on and so forth. So if you multiply a matrix by, say, a scalar value 2, and you calculate the determinant of that matrix, you will find out that the answer you will get will be that same 2 multiplied by the determinant of the matrix when you have not performed the scaling operation on the row or column. We'll be looking at some examples on this later, so this is just an explanation for now. So you can also perform addition, subtraction, as the case may be, on the row or column. So adding a multiple of one row or column to another does not change the determinant. It doesn't change the determinant. So it can be done, like I told you earlier, it can simply be done in order to work towards achieving the solution to a complex problem. So the second property we would like to talk about under these properties of determinants is the determinant of a matrix with repeated rows and columns. So if a matrix has 2 identical rows or columns, its determinant is 0. You have 2 identical rows, maybe the first row is 1 2 3, the second row is 1 2 3, then the determinant will give you a 0. And you see that is talking about, let's say, a 2 by 2 matrix. For example, you have the first row is 1 2, the second row is 1 2. You understand? So it shows that you have 2 identical rows. So when you compute the determinant of that, you can try that out. You'll find out that the determinant will give you a 0. So the third property we want to talk about is zero determinants. So if the determinant of a matrix is 0, it implies that the matrix is singular, meaning it does not have an inverse. So we'll also talk more on this later, and when we begin to look at how we can solve systems of linear equation using matrices. All right, we are still discussing determinants. Of course, determinants do have applications, and you can use determinants of a matrix to check the invertibility of a matrix. That is to say, a matrix is basically invertible if the determinant is non-zero, so it can be solved. So another application area is in the computation of the area and volume of shapes. Another very useful application of the determinants is solving systems of linear equation. So we'll be looking at some couple of examples in this area in the next. Okay, so with respect to area and volume calculation, take for example, you want to calculate the area of a parallelogram in 2D space defined by 2 vectors given by vectors u and v. So this is vector u and this is vector v. So how do you calculate the area of the parallelogram in 2D space? Solution. So the area of the parallelogram can be calculated using the determinant of the matrix formed by these 2 vectors. So when you look for the determinant of the matrix formed by these 2 vectors, you get the area. So since it forms a 2 by 2 matrix, what you do is to say 3 times 4 minus 2 times 1, and that gives you 10. So basically, the modulus of that value gives you the area of the parallelogram. So the area is 10 square units. So another example, let's calculate the volume of a parallelepiped in 3 dimensional space defined by three vectors given by vector v, vector u, v, and w. As this is vector u, this is vector v, this is vector w. So the solution to this, I mean the volume of the parallelepiped, can be calculated using the determinant of the 3 by 3 matrix formed by this vector. So the determinant of the 3 by 3 matrix formed by this vector can be computed to determine the volume of the parallelepiped, and done appropriately using steps earlier discussed. You see 1 and the determinant of these, 3 and the determinant of this and these, 2 and the determinant of these, spread as displayed here. So will result, if done appropriately, in the value 5. So basically the modulus of that value of the determinant will give you the volume of the parallelepiped. So the volume of the parallelepiped is 5 cubic units, since the determinant is 5. So the inverse of a square matrix A is another matrix denoted by A raised to power minus 1 or A inverse, such that when A is multiplied by its inverse, the result is the identity matrix I. So mathematically, the relationship is expressed as A inverse equal to A inverse A, and it's equals to identity matrix. In other words, it doesn't matter which one comes first. Either you multiply the matrix with its inverse, or you multiply the inverse with the matrix, it will still give you an identity matrix. So a matrix has an inverse if and only if it is non-singular, or if the determinant is non-zero. If the determinant is 0, then it has no inverse, and you are unable to proceed with such kind of solution. So now there are of course various methods to finding inverse of a matrix, and in this lecture we'll be looking at 2 different approaches. So the first approach is using the adjoint method. So for example, let's consider this 2 by 2 matrix. So how do you find the inverse of matrix A? So basically, using this method, the inverse of this matrix will be equal to 1 all over the determinant of the matrix multiplied by the adjunct of the matrix. Adjunct, well, in some other textbooks you have it as adjugate, so it is the same thing. So that shouldn't confuse you. All right, so the first step here is to find the determinant of matrix A. And the determinant of matrix A, of course, is A multiplied by B minus B multiplied by C. And that's it here. Then, how do we find the adjunct of A? Now, as a simple principle or simple rule, the diagonal from the top to the bottom, you interchange the elements there. In other words, you bring element D to this point and you take element A and you put it at this point. So that is the first thing you do to have the adjunct or the adjugate of A. So the next thing you do is you simply change the sign of the elements on the diagonal from the bottom. Of course, your left hand side from the bottom to the top and right corner. So that means you interchange this and you simply change the signs of B here to minus B. You change the sign of B, C here to minus C. So if it were minus here, you change the sign to plus. If it were minus here, you change the sign to plus. So whatever the sign is here, you simply change it on these two elements. All right. So now the adjunct of A, this is it, is equal D A have been interchanged as appropriate, and the sign on C B have also been changed as appropriate. So this is the adjunct of the matrix A. All right then, let's just attempt an example. Okay, now find the inverse of the matrix C, and these are the elements in the matrix C. So how do we do that? Do not forget the formula and the method we have just considered. The inverse of the matrix C will be equal to 1 all over the determinant of the matrix multiplied by its adjunct. So now, first thing to do is to calculate the determinant. All right, that should be something simple for you to do now. So that will be 2 times 3 minus 5 times 1. So if done well, you should get 1. So now find the adjunct of matrix C. So the adjunct of matrix C is found by interchanging this diagonal elements, and 3 comes up here and 2 comes down here. So then you also change the signs of this diagonal, and negative sign comes here and negative signs comes here too. So now the inverse of matrix C would be 1 all over the determinant of the matrix multiplied by the adjunct. Of course, the determinant is 1, so 1 all over 1 is 1, and this is the adjunct. So when you multiply 1 by the adjunct, you have this. So this is the inverse of matrix C. So let's consider the second method. The second method is about using elementary row operations. So for a m by n matrix, this should be m. Maybe I just don't like writing m, or I just simply just interchange them at times. Please don't mind that avoidable error there. So now to use this method, we find the inverse of a matrix A using the elementary row operation by following the steps. These steps. So the first step is to form an augmented matrix. So it will be in this form, a matrix, then you find something like a dotted line and you augment that line. When it is in that form, we call it augmented matrix. In other words, you have augmented the main matrix with an identity matrix. So where I is the identity matrix of the same dimension as A. In other words, if A is a 3 by 3 matrix, then the identity matrix will also be a 3 by 3 matrix, having 3 rows and 3 columns. So the second thing is to perform row operations to transform the matrix itself into the identity matrix I. So the matrix that I is transformed into during this process will be the inverse of the matrix. All right, let's solve an example related to the second method. So find the inverse of matrix A using row operations. All right then. So this is matrix A, and these are the elements in matrix A. So the first step here will be to augment this matrix with an identity matrix of equal number of rows and equal number of columns. So that's done implies that matrix A have been augmented with an identity matrix I, and that will give us something like this. So this is matrix A, these are the elements in matrix A, and this means you have augmented matrix A with an identity matrix. Of course, you do know what an identity matrix is now because we had defined it in our previous lecture. So that is the first step to do, and you've virtually done nothing. You've virtually changed nothing other than just augmenting matrix A with an identity matrix. So now the next thing to do, which is the second step, you then begin to eliminate the elements below the pivot in the first row and above the pivots, whatever you take as the pivots, in the third row or in the last row. So in that regard, it means that you begin to perform row operations on this matrix such that what you've got here becomes an identity matrix. That the diagonal elements will now be 1, 1, 1 each, and the off diagonal elements will be 0, 0. And as you do that on this matrix, of course, this identity matrix automatically gets transformed into the inverse of this matrix. So how do we go about that? Now look at this matrix vividly. In order to make you just perform row operations on this matrix such that the off diagonal element is transformed to 0. So let's take, for example, the elements in the third row and first column, this 5. So you want to make this 0. So you perform the row operation on this to make it 0, 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 row operation on this location to make it 0. So let's start from this. In order to do that, you then kind of program your row operations to eliminate 5 and make it 0. So let's choose a pivot. Here, let our pivots be row 3. So what do we do on row 3, and how do we manipulate row 3 to transform this 5 to 0? So our pivot is row 3. So now let row 3, the new row 3, be equal to the old row 3, which is this one. This will be the new one. This old row 3 minus, when you multiply 5 with row 1 and you then subtract row 5 multiplied by row 1 from row 3, you discover that this becomes 0. Just that's simple arithmetic. Now if you do that, you then have 5 times 1, that will be 5 here, then 5 minus 5, that will give you 0 here, and that is what we've got here. So basically, you write down your pivots, and of course you are not performing anything on this, any operation on this, so you write it down. And the row 3, which you want to perform the row operation on, of course will be changing. Each of the elements in the row will have to change as you perform the row operation on it. So now 5 times 2 will give you 10. So 6 minus 10 will give you minus 4, and that's what we've got here. So 5 times 3, that is 15. So 0 minus 15 will give you minus 15. That is what we've got here. All right. So 5 times 1 will give you 5. 0, of course, row 3 here what you've got here is 0. So 0 minus 5 will give you minus 5. All right. So now, row 1, you have 0. 0 times 5 will give you 0. So, and here you have 0. 0 minus 0 will, of course, give you 0. So that's what you've got there. Now, 5 times 0 will give you 0. So 1 minus 0, of course, this is row 3, minus what you've got here, times 5. So 1 minus 0 will give you 1. So we have successfully performed row operation on this to achieve our aim of transforming what you have here to 0. So we then want to transform, of course, what we do have here also to 0. So what do we do on that? We also perform row operation. Of course, you can perform 2 or 3 row operations simultaneously. We want to transform this to 0. Let's also try to transform this to 0 simultaneously. So what do we do on this to transform it to 0? And what do we do on this to transform it to 0? In order to transform this to 0, let's see what we can do. We can say, of course, that row 3 equal row 3 plus 4 multiplied by row 2. So row 2 in this case will be the pivot. So you won't change anything on row 2. Okay, so that is what we want to do to transform this to become 0. And of course, when we do that, you discover that row 3 here is minus 4 and plus 4 times row 2. That's 4 times 1 will give you 4. So minus 4 plus 4 will give you 0. Of course, this will become 0. So you also do, you perform same on this third column, same on this first column of the identity matrix, initial identity matrix, and you just do that on and on and on. So now, in order to get 0 in the second column and first row elements, then we perform another row operation. So how do we get that? So let now row 2 also be the pivots. We won't change anything in row 2. That means it is our pivots. Then our row 1 now, our new row 1 will be equal to row 1 minus 2 times row 2. So now row 2 here, this element is 1. So when you say 2 times 1 gives you 2, then you now say 2, which is row 1, minus 2, it will give you 0. Of course, you can also perform that here, and you will discover that nothing changes. Okay, row 1, new row 1 will be old row 1, that is 1, minus 2 multiplied by 0. Of course, 2 multiplied by 0 is 0, so you will still have 1 there. Okay, 1. So now, if performed well, this row operation will result into these values. If done well, this row operation will result into these values. So you then see that as you perform the row operation, these diagonal elements have now become units. The only problem now to solve is to ensure that this element and this element also becomes 0. So, well, it is neater to perform 2 row operations at once. Limit it to 2. Don't perform 4 row operations all at once. It may become messy. All right. So the next step is to transform the element in the first row and third column, as well as the second row and third column, to 0. So the row operations to perform on them have been outlined here. So we'll be performing 2 row operations at once to transform the elements to 0 from the previous slide. So the procedure basically is just as explained while we started with transforming the element in the first, third row and first column to 0. And so that is just the basic approach in performing the row operations. So now, if done well, these row operations, it will transform, of course, the first row element in the third column and the second row element, third column, into 0 as it is. So in all, you'll discover that what you've got on this side of the augmented matrix is now an identity matrix. And of course, what you have on this side have become transformed from an identity matrix to inverse of the matrix that was initially on the left hand side. So then this is an identity matrix. So then this is an identity matrix, and what you've got here is the inverse of the matrix. So simply writing it out shows that you have been able to use the row operation method to determine the inverse of matrix A, which is this. All right, this is classwork, and you can just play around with this and let's see what you get. All right, next let's look at applications of inverse matrices. Okay, the first application is that inverse matrices can be used to solve systems of linear equations. So now, how do we do that? So what we do is to transform the system of linear equation into matrix form in this order. And of course, the solution to the system of linear equation will be to determine what x and the variables are, x and y. So the solution will be in this form, where x equals the inverse of the matrix multiplied by the solution. All right, let's just see an example and let's solve that. So this is a system of linear equation. So I want to solve this problem using matrix inversion. So the first step is to write the system of this linear equation in form of a matrix, and that is in this form. So your matrix will be the coefficients of x is 2 and 4. You've got that here. And the coefficients of y is 3 and 7. You've also got that written here. So now the unknown is x and y, and that you've written down. Then b is the solution to this system of linear equation. So there you go, 5 and 10. So now the first thing to do is to find the inverse of this matrix. Now you can use any method you like. I prefer to use the adjoint method because it is simpler. All right then, so using the adjoint method shows that the inverse of this matrix will be equal to 1 all over the determinant of this matrix times the adjoint or the adjugate of this matrix. So what then is the determinant of this matrix? The determinant of this matrix, of course, is 2 multiplied by 7 minus 4 multiplied by 3. So 2 times 7 is 14 and 4 times 3 is 12. So 14 minus 12 gives you 2. That means the determinant of this matrix is 2. Then what is the adjunct of this matrix? It means you have to interchange these two diagonal elements, and 7 comes up and 2 goes in here. Then you also change the signs of these two elements. So this becomes minus 3 and this becomes minus 4. So the inverse of this matrix will then be the adjunct divided by 2, and that is why you have 7 all over 2 minus 3 all over 2 and 4 all over 2. That's minus 4 in this case because you are now multiplying, you are now dividing the adjunct by the determinant, which is 2. So that will be minus 4 divided by 2, and that will give you minus 2, and this 1, this would have come down. That will be 2 all over 2, and that will give you 1. So now the solution to this system of linear equation, which have now been transformed into the form of a matrix, will be x, this one. So will be x equal to the inverse multiplied by the solution, which is b. So you perform multiplication operation on this. So in order to do that, this multiplied by this, and this multiplied by this, this multiplied by this, and this multiplied by this. So you just simply add them up. So that means 7 all over 2 times 5. That will give you 35 all over 2. Then this will be minus 3 all over 2 times 10, and that will give you 15, minus 15. So when you work on this, that is 35 all over 2 minus 15, your answer will be 5 all over 2. So for this, it will be 5 times minus 2, that will give you minus 10, and 10 times 1 will give you 10, of course plus 10. So minus 10 and plus 10 will give you 0. So looking at the fact that x is y and z, of course your x now will now be 5 all over 2, and your y will be equal to 0. So that is the solution to the system of linear equation using matrix inversion method. All right, let's now move on to looking at higher order of the system of linear equation with 3 variables. So in order to solve this system of linear equation using matrix inversion, the first step we take is to express this system of linear equation in form of matrix. Ax equals to b. All right, so where the coefficients of x here is 1, 2, and 3, 1, 2, and 3. The coefficients of y here is 2, 3, and 1, 2, 3, and 1. The coefficient of z is 3, 4, and 2, 3, 4, and 2. The solution vector is 1, 2, and 3, 1, 2, and 3. And of course, the variables are x, y, z. So now we have done this successfully. That's the first step. So the second step is to find the inverse of matrix A and multiply with the vector solution, that is B. So then finding the inverse of this for a 3 by 3 matrix, how do we go about that? So now, of course, using the adjoint method, then we will first of all find the determinant of this matrix. So recall we've done this earlier. So to find the determinant of this matrix, remember the equation we generated the other time. Just plug in the each elements in position where we represent this as A, B, C, D, E, F, and so on and so forth. So Well, just substituting and plugging in the value, or just do not be bothered with this. Just basically look for the determinant, calculate the determinant of this the best way you can, really. Well, if done well, as appropriate, the determinant of A equal -3. So now, since the determinant is non-zero, that means the matrix A has an inverse. So if it has an inverse, of course, we are at liberty to continue with our solution. All right then. We then want to move on to the next step. The next step is to find the inverse of matrix A. So how do we find the inverse of a 3 by 3 matrix? Using the adjoint method. Excuse me. All right. So now, the adjunct, the inverse of matrix A, of course, equal 1 all over the determinant of matrix A multiplied by the adjunct of matrix A. So how do you find the adjunct of matrix A? I'll just show you a very simple formula, and you should be fine with that. So the first thing to do in finding the adjunct of this matrix, of course you can use cofactor method, you can use different methods, but I like this method because it is simple and direct. So what you do is to take this first elements in the first row and first column, and right, so and then you can let's say cover the elements relative to the row and the column. So what you are left with is a 2 by 2 matrix. So you then look for the determinant of that 2 by 2 matrix you are left with. So the determinant of that 2 by 2 matrix will be the first element in your adjunct, or the adjunct of matrix A. So that will be E multiplied by I minus F multiplied by H, and that's what you've got here. So then you need to alternate the sign as you move on. So having done this, the next one you have to alternate the sign, so it will be minus. So however, having treated that of the first row, you will also have to cover the second row, and you'll be left with this 2 by 2 matrix BCHI. So but because you must alternate the signs, so instead of BI minus HC, it will have to be HC minus BI, because the sign must be alternated. Otherwise, you can say minus BI minus CH. And when you put that in brackets and you multiply that out, you still get CH minus BI. So now, because you've alternated this sign, this one will remain as normal as it should be. So you won't have to alternate the next one. And the next one, of course, will be to cover the third row. And the matrix you will be left with is this 2 by 2 matrix, which is B multiplied by F minus E multiplied by C. Because you are not alternating the sign, so that remains the way it should. BF minus EC or CE. The next one also you will alternate the sign, but how do you get the next one? So you get the next one by covering the next element, which is the element in the first row and second column, and you can cover also the element relative to this B with respect to the rows and the column. So what the matrix you'll be left with now is this DFGI elements. So because this you alternated this sign to negative, this is positive, normal, this also will be alternated to negative. So because of that, it will now be GF minus DI alternated. So the next one will be, okay, you also cover this up and you are left with 2 by 2 matrix ACGI. So the matrix of that will be AI minus CG. So you are not alternating that because you alternated this. So the next one will be alternated, and you will determine that by also covering that of the third row. So you are left with matrix 2 by 2 matrix ACDF. So because you will be alternating the sign, instead of having AF minus DC, you will now have DC or CD, CD minus AF, because the sign must be alternated. So the next one will not be alternated. And you also determine that by taking the element in the third row, in the first row and third column, and covering the element relative to that along the column and along the rows. So you'll be left with this matrix, because you will not be alternating the matrix of this now. That will give you DH minus EG, normal. So the next one will also be alternated, and that will be, you cover the next row now, that will be BG minus AH. So, and that's how you move on and on until the last one now. So the last one is gotten by covering the elements in the third row, and because you alternated this sign, you don't have to alternate the matrix of this 2 by 2 matrix, and that will give you AE minus BD here. So that is how you determine the adjunct of a 3 by 3 matrix just easily. So when you perform all this by simply plugging in the values, you can just calculate them out individually. Of course, it is just a simpler way of doing the cofactor. It's a simpler way of the cofactor method, basically. So it has just been simplified here. All right then. Well, plugging in the values and calculating the answers as appropriate. If done well, you should get these values. And EI minus FH, which should be here, being 2, this becomes 2, this becomes minus 3, minus 1, 2 minus 3, minus 1, 8 minus 7, 2, minus 7, 5, and minus 1. So this becomes the adjuncts. So do not forget that the inverse of the matrix is 1 all over the determinant multiplied by the adjuncts. So you then have to divide all the elements here by minus 3. So if done well, you should get something like this as the inverse of the matrix A. All right, then the next stage now is to simply determine the solution to the problem. So the solution, of course, is in this form. X will be equals to the inverse of matrix A multiplied by vector B, which is the solution to the system of linear equation. So then this is the inverse of matrix A as determined in the previous slide, and this is the solution vector in the matrix form. Okay, so when you multiply this by this 2 by 1, this 3 by 1 all over 3, that will be the solution to X. This by this, you multiply this 1 by minus 8 all over 3, 2 multiplied by 7 all over 3, and 3 multiplied by minus 2 all over 3. that gives you the solution to y. And this is it. Now, for z, you multiply 7 all over 3 by 1, 5 all over minus 5 all over 3 minus 5 all over 3 by 2, and 1 all over 3 by 3. And if done well, you should get 2 all over 3. So the solution of the system to the system of linear equation using matrix inversion method is x is 5 all over 3, y is 4 all over 3, and z is 2 all over 3. All right, so, well, other applications of matrix inversion is useful in computer graphics, that is transformation. Matrices are often used to perform operations such as translation, rotation, and scaling on objects. So the inverse of a transformation matrix is used to reverse these transformations, which is crucial in rendering and manipulating images and objects. Computer graphics, very, very applicable. And also in control system engineering, matrix inversion also finds very, very useful application, particularly in finding the transfer function of a system. So, well, you should be able to play around with these applications when you get to higher levels in your undergraduate studies or even postgraduate levels. All right, this is a classwork. It's 3 by 3. This system of linear equation, of course, can be transformed into a 3 by 3 matrix when converted into matrix form. So you can play around with this and solve it, and let's see how it goes.